Okay, then let's start the last session. So my name is Janine Gugelhorn. I'm a postdoc here at ICMAB in the Mulfox group, and it is my pleasure to introduce the last speaker, Patricia Abellan. She is a CNRS researcher at the Institute of Materials, Jean Roussel at Nantes University. She obtained her PhD in material science here at the Autonomous University of Barcelona and ICMAB in 2011, and she held postdoctoral positions at the University of California, Davis, and Pacific Northwest National Laboratory, and a staff scientist position at SuperSTEM Laboratory in Dasbury. Currently, her research focuses on the study of defects at interfaces on functional materials and their relationships with properties used in electron microscopy and the use of the effect of the electron beam in solid and liquid media to investigate the radiation physics and chemistry of nanomaterials. So the stage is yours.
Thank you. So, well, first, I'm really excited to be here. I think last time I was here in this was for my PhD defense in 2011. Yeah. I thought I came before, but no, I have my PhD advisor is sitting down right there. So this is very exciting. So yeah, yesterday we talked, I work in Nantes, also in an Institute of Materials. I went to different centers, mainly focusing in electron microscopy, but now I came back to university and a center of material science. Have to point here. Click. Yes. Where I am? Oh, okay. Yes. So yesterday we were talking about this, and there was some confusion that maybe it was a statue. Actually, the famous elephant of Nantes is a machine that throws water. Children love it. Yeah. So, so yes, it's a very beautiful town, but yeah, it has also the EELS machine, which is quite famous. Okay, so what I'm going to be talking about, I have two talks. The first one is a little bit lighter still, and I have tried to leave it to give a state of the art, a little bit of what has been the development in instrumentation that has been needed to actually do EELS in liquids, and also what are the problems that you find, because every time you fix something and then you find a new problem. This is usually what happens when you do in situ, and where we are right now. And this is a really good moment to do EELS in liquids because there are many problems that have been sorted that were there for a decade and a half that now they are almost gone. So just to say that there is, for the last decade and a half or a decade, there has been a field of research in electron microscopy. There has been a renaissance because there were some works before looking at liquids as solutions and solid liquid interfaces in electron microscopy. And these are some of the first papers. My main work is in water. So here I have focused the bibliography in water and aqueous solutions, but there are a lot of work. So this is the first time that the metal-organic framework, so big macromolecular structures were synthesized in situ in the microscope. And also the first time that oxides were synthesized in the electron microscope, aqueous batteries, so looking at SEI layers and how dendrites grow. And then also in biomedicine, I choose this example because this is one example where they saw a new process for biomedicine. So this is how micellar structure form, and it was like a new way of forming. And then it has been really cited by the community outside electron microscopy. So it was published in Nature Chemistry, but then it has had an impact in other fields of research. So I wanted to put it just to say, because at the beginning there was this feeling that, well, it was a bit like the beginning of cryo, the blob law science. But now we are starting to produce results that actually are helping other research fields. So the first work, and then I realized when Juan Carlos was doing his presentation that this is only 1 year after the invention of electron microscopy. So just 1 year after the electron microscope came out, you can find works where people were trying to look at liquids. So they were trying to stick a liquid there and see what happened. Because as you know, we work in high vacuum conditions. So you need to separate this from the rest. And the way that they were doing this at the beginning was using parafilm seeds. and then aluminum foil, so any trick that could work. But then these efforts were abandoned quite quickly because of the resolution. The resolution was really low. So, but yes, they were like trying like really from the beginning of electron microscopy to put solutions and liquids in there. And then it was this the nominal paper from the group of Frances Ross in IBM, where in 2003, they used all the microfabrication developments that were available at the time and the idea of doing this environmental cell, and they managed to enclose the liquid using silicon nitride membranes in silicon chips microfabricated in clean rooms, and this really started again the field of liquids. Now, this idea, to be fair, was also there are papers like 70 and 60 where people were trying to do a machine like that to separate the liquid environment from the column of the microscope, but the technology was not really there to get the high resolution that they got in 2003. So the field, the way that we know it, it started after this nominal paper, but people have been trying for decades to look at liquids. And now, so there are companies that sell these holders, so you can buy a holder and you can just look at liquid in your electron microscope. And we recently published a tutorial, but this is not only for liquid, it's for in situ and for Operando. And you have a whole myriad of properties that you can combine to look at materials in situ conditions. Operando is a bit tricky because then you really have to reproduce things, but yes, closer to the conditions where processes really happen. And then this is a little bit of the interaction between this. So you can do liquids combined with a biasing field. You can do an electric field. You can heat. You can do biasing with cryo. And this, for some fields of research, is really important. And then magnetic. So all these things now you can also combine them and put several stimuli or an environment and stimuli simultaneously. And you can buy these things commercially, which makes it much more accessible to everybody. And then something that is important is that because it is a holder, you can transfer it from one microscope to another. So you can, all the capabilities that you have in your microscope, you can apply it in this material the same way that you do it with solids, more or less. And I put this example because this is there is still renewed, so they keep improving these holders. So just in 2023, 2021, I think there is like, but I couldn't find electrochemical data, but there were these holders where the reference electrode, they took it out from the viewing area where your reference is going to be modified by maybe the radiolysis or the processes that are happening, and then they took it a bit off the chip. And this, what gives you is a real bulk reference electrode for electrochemistry, so a much more accurate representation of what is happening. So this is just to illustrate that this was not done like some years ago, and now this is done, that they keep updating, and there is a lot of research that usually comes from the needs of users and the work collaboration with laboratories to make these things much better. This actually is a custom-based design, and now there is also a commercial one. This one is a company, but it also comes from the collaboration with groups in Germany and so on. And there is another technology, so it's not only that you have to buy this holder, there is also a way of enclosing your liquid in any microscope, which is using graphene liquid cells. So this is a technology, and there are different cells in this way. So I modified this figure, I add one of them because they keep also getting more and more complex. So the idea is to take 2 sheets of graphene. This was the original paper in 2012. And then you can enclose your liquid, you let it dry, and then just by the bonding, you get these pockets of liquid, and then you can put in your microscope and study them. And some of them, this works really well for biological samples. And there is a paper where they prove that you can get higher tolerance than actually in cryogenic conditions in some cases, just by using graphene, encapsulating them. And then there is like this type of hybrid cells where you combine graphene with other materials, and then you have predetermined wells with a thickness of the liquid. So these are much more controlled systems that you can use. And then the good thing is that, well, you have much higher resolution. It's easier to do EELS here because you have less scattering of the liquid. These are thinner samples. You don't need a holder, but the thickness of the liquid is much more difficult to control, especially in these approaches here. Here is a little bit better. It's not so easy to do the mounting when you get started. It's like, it needs like some time of getting used to this. And then, as we will see later, there is some problem about the concentration. If you're looking at solutions with precursors or with something that is not just a liquid with particles, you can have problems of keeping the initial concentration that you have, but I will show that later. So what I said before is that since you are using holders or you are using liquid cells that you can prepare, this is basically just sample preparation at the end of the day. So you can really use well-established techniques. And these are the first paper on diffraction. And diffraction is a good idea. Well, reciprocal space has a lot of very useful information, but also it costs much less electrons to do than an image. So you can go, these are low-dose techniques, liquids that usually being sensitive. So if you can take information that using much less incident electrons, this is always good news. So you can go down 4 orders of magnitudes. You can do tomography. There were 2 papers simultaneously. But what about EELS? Okay, so now we are going to go to how do we do a spectroscopy. The first EELS paper, I have put it together with the first EDX paper, but the first EELS paper was almost from the beginning, so 2012, and it looked like that. So this is probably not the most impressive spectra you have seen in this workshop, but this was really challenging at the time. So this is from Katie Jung-Johan. And yeah, we were in the same group at this. And then the first EDX, it was done a bit more recently. So for these 2, what had to be done was different. So in EELS, you really need to reduce your multiple scattering. So it's all about the thickness of your sample. For EDX, you needed to micro machine things because the detector, if you can with electrons, now I'm thinking not in neon wave, but in the other microscope, so you can you go through the sample, and then your EDX detector is going to be in the same, so before the sample. And these micro machines, so the silicon nitride, the silicon chips, they have like really sharp edges usually to go down to the silicon nitride membrane. And so usually they clip the signal that goes to the EDX. So it was just a matter of increasing the collection because we were not letting the X-ray to reach the detector. And now you can buy holders for EDX, and you can buy chips that are micro machines with all these areas clipping your detector for EDX. So the problem of EDX was more or less fixed. It's still you're losing X-rays, but you can do EDX. And then with EELS, there has been a progression since 2012. So I'm going to show some of the common uses of EELS that we were doing from the beginning. One is looking at thickness. So Juan Carlos already said you can measure thickness with a spectroscopy. And I have a couple of equations here and the next slide, but we're not going to go through them. So, okay, so this is the log ratio method. So this is the typical method to look at, to measure thickness. And if you want to measure relative thickness, so in terms of inelastic mean-free path of electrons, you just need to integrate the intensity of the Serolo's peak, the intensity of your whole spectrum. This is done with an extrapolation. And this is done in the software that we use usually in electron microscopy. So it's done automatically. You have an EELS spectrum and you said measure relative thickness, and it does this calculation and gives you a value in terms of lambda. And usually, if you have a solid sample, you're going to have things that are much thinner than this. So you see your Serolo's here is really small compared to this signal, and we have not really reached the plasmon yet. So these are very thick samples that we had at the beginning in the field. So these are non-aqueous electrolytes for battery research. And this is for the MOF paper. And here also, and here you also see the Serolo's peak and a huge plasmon. So these are very thick samples, and yet you can do a movie like with micrographs showing processes. So this is not like a solid, this is much less dense. So you can go to 1 micron and still be electron transparent. You will lose some, but you can do movies. But for a spectroscopy, it's critical. With a plasmon like this, you're not going to see much. than in the core loss or in the low loss, for that matter. Okay, so yes, you can measure your thickness in terms of inelastic mean-free paths. This means that you're going to have a lot of multiple scattering. But then if you want to calculate absolute thickness, so you want to know what is the thickness of your liquid in nanometers, which is something that we understand a little bit better, then these are the two usual methods to do that. And without going into this, so this is the lambda inelastic mean-free path, the Jakubowski method, and the Mallis method. This is usually what we use to look at the thickness of samples. And then there are these two magnitudes here, and this has been empirically measured. So that this equation came from an empirical measure. They work really well for metals. They work for almost all semiconductors, but for insulator, these two methods fail. And then for the case of water, what it turned out is that you actually need to revisit this. So there is this paper where they look at the inelastic mean-free path for water and then realize that everything that we have been doing measuring the thickness has been underestimated by quite a lot. So there is a measurement from Ray Egerton on crystalline ice, and they agree with him, so their calibration give more or less the same values, but if you compare to the liquid water that you get, so this is not the thickness, this is this energy and the sigma, so these the two values that you have to input into this method to calculate the thickness. So we are systematically including values that are going to give you a much lower thickness, and then this has to be recalculated for the primary energy that you are using. And then, so good news is you can use ice, it seems, to measure this if you cannot do it in water, and then you go. Or you can use what they use that I will show later. They have a predefined thickness of water that they know exactly, and this is like a new technology that has come out recently, and then to do this calibration. Another use of EELS is to prove whether there is liquid or not, and this was one of the problems of graphene cells. So if you're not using the silicon nitride technology, but you're using graphene cells, especially the first models where you have like two graphene seeds together, it can be really tricky to find actually the liquid. And one method that at the beginning that people was using was to irradiate it for long and then see that there were like bubbles, but this means that you are decomposing the water, you don't have water anymore, so you want to avoid this. So another way to do it is just look at oxygen in the core loss, or even better, look at this peak in the low loss, which is usually labeled as an exciton for water. It's around 8.4, 8.6 electron volt. And this tells you that you do have water in this pocket. And then it's the low loss. So again, you are saving electrons because you need less electrons to look at this energy loss range, so it's much better. And then I put this because I saw that, yes, I come back.
Ideally, for doing in situ, you would need a chromated microscope. In this case, for this, you need
for this
a monochromator.
8 electron volt is, well,
it's not necessary.
You need thin layers of liquid, but for the most part, no monochromator.
It's not necessary.
I think you can see 8 electron volts you could see with a non-monochromated scope if your liquid is not too thick. Yeah, it always helps. Well, especially because since they are sensitive materials, it allows you to really fine-tune the dose really precisely. The monochromator, this is also a way you can use it. Okay, these are not common use of fields in liquids, but these are things that has been done. So if you have a thin enough layer, you can actually do vibrational spectroscopy. And if there are questions on this, I'm going to redirect them to Johan, because this is his work with Robert Klee and Juan Carlos. So they look at vibrational modes in water and deuterium water, so that they change the hydrogen by deuterium. And then also, this is also Robert Klee, he has been looking at changes in temperature in liquids. So you can do this using like very thin layers of water. So anything that you have seen in the previous talk, you potentially you could do it here. Okay, I'm going to go back to graphene cells because this is like the additional problem that they have. So you have reduced scattering, and then you can see like beautiful fine structures, so where you can distinguish the cerium 3+ from the cerium 4+, so you can do like, yeah, then you can apply core laws and look at the fine structure here. But, well, it doesn't allow at this moment of time for doing operando measurements. But at the same time, this work, one of the main points that it had is that it actually changed the initial concentration of your solution, and it makes it really difficult for you to control it. So if you are looking at something with solids, so any growth of particles and things like that, you are not going to know what is the concentration that it has. Is usually much higher than what you think. And this is the way these things are loading, because you have to put them together and then wait until this dry, and then some of this liquid is going to go out, most likely. But what they measure is that if they started with 14 millimolar the cerium chloride, and then this means that you have 1,300 atoms of cerium. Well, there is a ratio of 1,300 for 1, approximately. This is the nominal ratio. In EELS, you're going to measure something like, well, this is not, like 4, okay? And if you decrease the concentration, okay, this is also 4. If you go much lower, then you get 20, the ratio from one atom to another. So this is like really drastic. And what it is worse is that, well, the solubility of some of the solutions that you're putting there might not actually handle this. So in this case, the solubility of cerium chloride in water is 4 molar. And this means that the ratio of 14 to 1, this is like the minimum you have to have. And some of this is not really a liquid. So if you look at this, 20, okay, 20 to 1, yes, but 4 to 1, 3 to 1, this is not really a solution anymore. You have some kind of part, like there is some water trapped in there, but it is not really a solution. So this can be really complicated. I put this, I don't know a lot about it. So I discovered while doing this presentation, I found out that now it is possible. So they came out, this is the group of Jaime Isang in Berkeley, and they have developed these new films. This is former films, it's a polymer. And with this, so what they were saying in this paper is that you can actually have high resolution. So it's like similar to the benefits of graphene cells. So high resolution also for spectroscopy, but you can also do operando. So they put an electrode in there. So this would fix the problem of the graphene cell where you cannot actually put an stimulus. Yes. Yeah.
So they are doing graphene cells that transfer graphene cells to silicon.
In liquid, right? Yes. Oh, yes. So the comment is that not all the graphene cells suffer from the problem of getting an increased concentration when you load them, because some of them are loaded in humid conditions. You don't let them dry outside. Yes. Sorry, that's a good point. Thank you for saying. Yes, if you can load your samples in humid solutions, then it will have to be calibrated. I'm not sure, but yes, most, yes.
Because they published in PubMed, they are now developing folders that is compatible to that sort of prototypes, and we can actually use graphene instead of silicon nitride chips. So they are transferring graphene to silicon nitride chips from that.
Yes.
And can grow gas or liquid or all of that.
So this is like, yeah, like the hybrid cells. Can I go back a lot with?
It's not available commercially.
No, but there was a method, one of the graphene cells that this one here is a silicon nitride graphene hybrid. Is this what you are saying? Ah. Okay, so you have a well. Graphene, a well. Yes, okay. So yes, it's a similar idea to this. They did this before with boron nitride. Yeah, and then boron nitride and then graphene, and then you can do the same. So this is the idea also of, yeah. Wait, it is bonding to the silicon nitride? Yes, okay, because for a moment silicon doesn't work. Yes, so it's the same idea that this works here.
There is no silicon nitride name. It's graphene only. Electron has two graphene.
So where does it bond? Because they are separated, no? If you have a weld?
They chip, so they bond it to silicon chip instead, not silicon nitride, sorry.
The silicon?
Yeah.
Okay, I haven't seen this. So the comment is, for those there, is that, yeah, they are developing something not commercial, not out there yet, where they remove the silicon nitride and then both sheets of graphene in a well that links to silicon. Yes, okay. And then with that technology, what I assume is that then you can maybe put electrodes and do things like that because it's silicon directly. Well, I don't know. We don't talk about that. It's not commercial, so we don't talk about. Okay, so yes, there is this here, which combines the benefits of having very thin layers of liquid and having high resolution and looking at fine structure in EELS. And then also, apparently, you can apply an electric field. I don't think they did electrochemistry, but they applied an electric field here. Okay, so I'm gonna go into trouble. So the main one is the bulging. So going back to silicon nitride, there is a bulging of the membrane. So when you put these things, you load them outside the microscope at ambient pressure, and then you put them inside your microscope, and then with the pressure differential, you're gonna have a bulging of the membranes. And this is a problem for doing spectroscopy because that means usually you have to go and work in the corners or in places where it is thinner. That means that your thickness is always going to be much larger than what you initially had, even if you put spacers or something. And then also it's going to be inhomogeneous, the area. So if you're doing maps, you always have this change on thickness homogeneously. So this was something that it was observed very early. So these are early Operando studies where Megan Wolf, the CISO, where she was doing like EELS and looking at different lithium compounds. And what she said is like where the main two obstacles at the time was there is excessive beam scattering because of this thickness of liquid, and the area is not very homogeneous, and then also because they are so thick, you need to increase your dose a lot, and these are beam sensitive materials. So in order to bypass this low signal to background noise for EELS, then you have to really put a lot of electrons in there, and this is not helping you with your electrochemistry. And there were some research at the time is like, what if we reduce the electrodes? But then you still have the bulging, so it doesn't really help with this. And then reduce electrodes also give all sorts of problems on the electrochemical part. Okay, so this is a sentence that I took from this paper. So they said that core loss EELS of the lithium is practically impossible to detect in the liquid cell. And it was true at the time. So this is 2014. You couldn't look at the core loss of lithium with EELS for doing this type of experiments. So there are now ways to reduce significantly the thickness of your sample and at the same time have homogeneous thickness of water to do like, well, of liquid to do your experiments. And this is one technology that came out, became commercial in 2023. This is a group from in DTU, Christian Molhab, that then they have done a spin-off of this. And what they develop is a technology on nanochannels. So this is something that is like maybe 200 nanometers, and then with silicon nitride all around, and a thickness that could go from 40 nanometers, 100 nanometers. You can actually choose the thickness before, and all the channels have this thickness. So you can look at liquid systematically from one channel to another one with the same thickness. And this, well, it's very easy to do spectroscopy on this, and you can look at different things. Okay, so this increased the reproducibility, and then it's compatible in their configuration with flow and heating very recently, and then they have been trying different things here that we couldn't do before. So yes, EELS with very high resolution, 4D extent, they give it a try, and so on. Okay, so we got one of these in Nantes. I got one of the electrochemistry with bulk reference electrode, and then another one to do systematic with the same thickness. And this is like, yes, so this is one of the chips after an experiment. Blue means empty, and then yellow is filled, so it's a bit counter. Yeah, this is optical microscopy. And what I was looking here is a rhodamine B dye in ethanol. And then you see the cross section. These are the single excited electronic states of the molecule, and then all these peaks here are higher energy excited electronic states of the molecule in solution. And yes, this is possible. This is not very difficult because you have this homogeneous And then you can do like a large area where you can really separate your beams and do very low dose and then average all these things and get it without even direct electron detection and things like that. You get like, and without trying very hard with the monochromated. We have a monochromated microscope, but usually I set it to get the thickness and so on. And I'm limited by dispersion, so it's like 150, 200 millielectron volts. You still see these things. Okay, so there are some problems with this technology. It's not perfect, these are channels. So you still have to get your sample in there. And yes, if you have nanoparticles, it could be a problem. So you need to look at nanoparticles which are smaller than the channel, so you can, yeah. But even if it is not nanoparticles, what I found is that sometimes like things happen that you cannot understand very well, because so things behave a bit different maybe on this. And what I was trying to do, because I tried ethanol, just because I had a spectrum for the literature I wanted to see, but what I really wanted to look was a rhodamine dye in water. And when I tried to do this, what you see is like this, like, so you have water, this is your 8.46 electron volt for water, but you have nothing here. You see, this is where this huge peak was in 2 electron volt, and this is the same concentration and lower concentration. Yes. We have a question.
Why do you want to see rhodamine in water?
Ah, very good question. Yes. Okay, I'm going to go into that. So first I tell you this, and then we're going to see why in water.
I don't know what rhodamine B is.
It's a dye. It's a molecule with a huge cross-section for optical spectroscopy, so they use it to calibrate everything. And you can see it so well that they also use it a lot in microfluidics to see fluidics, like where things go and things like that.
Okay.
Yeah, but for Raman, so yeah, calibrate things, and yeah, it has been really used in spectroscopy, but it's a very nasty molecule. But I'm gonna tell you, yes. Okay, so this you can see by eyes. So here, this is a filled channel when you have liquid in it, and this is when it is empty, and you can see that the silicon nitride outside and the silicon nitride inside, it looks the same, and you only see the membranes on the side, the perpendicular, just because you have a more, yeah, anyway, because of the atomic contrast and thickness here. But you really know when you have liquid in your channel if you are doing zeta contrast, so high angular annular dark field stem. And I knew I have water, so I could see it here, I could see it here, and no molecule. So what it seems is that you may have some kind of chemical separation that you try to put them in here, and then the water goes in and the rhodamine doesn't go, and I couldn't understand this. Okay, so why water? I mean, because you want to do this, if you cannot, then you quit, no? But why do you want to look in water? These dyes in general, it's not only rhodamine B, it's methylene blue, there are a lot of these dyes. They are like from the textile industry, they go into the water supply, and they pollute them, and you cannot get rid of them. There is a whole field trying to clean water from these things, and this comes from the textile industry. So the dye that we have to make the nice colors, but then it goes into the water, and for some of these, it is really, really difficult. So people are trying everything to try to get rid of it. My project is also on water, but yes, there is a big problem with these things. And I choose this one. This is very recent, but there is a lot of research that comes from, in radiation chemistry, there is a whole part which is like cleaning water from pollutants. And these are some nasty ones. And so you can irradiate things with different irradiations to try to break down these molecules and clean the water. And here what they do, so this is rhodamine with a catalyst. So you can try different catalysts, and then you can try different conditions in the solution with different acidities. And then you see that you cannot get rid of these things. So this is like the concentration of this, the one that gives the color. And then you need to really combine your catalyst with the right pH to kind of, so yeah, you need to find the right way of doing these things so that it is effective. And there is a lot of research on this. And sometimes you can just remove the color, because then aquatic life can live because they see the sun, because otherwise if this is like really bright pink, then yeah, everything dies. But yes, you can also get rid of it completely if you look at the higher. Anyway, so water is better for the experiment. And I found this, And the thing is that it is not the same condition. So when you have confined volumes, but this is real confined volume, so this is aluminum pores with 20 and 10 nanometers diameters. When you have something like that, then the properties of your solution are gonna change. And what I found is this paper where they have that the solubility of rhodamine in a mixture of ethanol and water can change. So this is like, I think zero is water, and then 1 is ethanol, so 100% ethanol, 100% water. 60, yes. So this is 60% water and 40% ethanol, and it's a sweet spot for this material where the bulk solubility of your solution increases, and then so that means you change the viscosity, and this has an impact in the diffusion. So when you have a confined environment, you don't have just the bulk diffusion, you have two regimes. You have the one closer to the membranes, that is a slow diffusion, and then in the center, there is a faster diffusion. And what you want is to increase your lower diffusion. Okay, so I have 150 nanometers channels, and this is what you can buy. You can buy 40 nanometers channel, and you are closer to this problem. But yes, I still try, and then this is the one here, so the 10 millimolar rhodamine with 60% water and 40% ethanol, and you can get your molecules in the channel. So it seems that we do have a little bit, even in 150 nanometer, a bit of confinement effect. And then, yeah, then you may have questions of what it is, the concentration that you have, does all the rhodamine goes, or we are, well. Now, the good news is you want to clean water, you can make them pass through this, and then it gets clean. Okay, so this is another way of getting thin layers of water to do a spectroscopy. So this is a group from UCLA with Chris Regan, and what they did is to do the loading. This is a very smart idea. This is in vacuum loading. There is also this other group in Canada, and actually they develop a commercial version of this. So this is something that can be purchased. So the idea is to do the loading of the samples in vacuum conditions, emulating the vacuum of the microscope, and then in this way, once you put it in the microscope column, you don't have the pressure differential. And then this is a bit convoluted to do, so they developed this device in this paper. This one, I guess, has a patent, so I don't know. But yes, they developed something like this to do their battery. But then if you do in vacuum loading, this works, and you can get a beautiful map of all the lithium phases. This is with MLS, so you do multiple fitting when you have all the phases of lithium in your RCI layer in operando conditions with EELS. And this is 2023, so it's really recent that they have been able to do this. And then I just put this. This is from the same paper, from the proceeding before the publication of the paper in microscopy and microanalysis, where they can see lithium core loss. So it took a decade, but now it is possible to look at lithium core loss in non-aqueous electrolytes and actually have a map, again, a very broad area. And I put this because I have to mention, so this didn't get widespread in the community, but it's another way where you can minimize bulging, and it's a similar idea. So this was a little bit before, so 2019. If you have a holder for flow, and most of the holders now come with flowing capabilities, you can do a trick where you can actually play with the pressure in your channels and change the pressure when it is inside the microscope, and then you can reduce the bulging. This is what they were proposing. It has not been adopted by the community widely, but this is something that they show that you change the bars, and then you can decrease the thickness of your layer and get a more homogeneous. So this could also work. Okay, so I put a warning here. This is one of these situations where you need to be very careful what you are wishing for, because we keep talking about how to reduce the layer thickness of your water, and you want to go to 150 nanometers, 40 nanometers. And now the problem is that if you actually want to do operando, you want to look at batteries, and this is going to affect your performance. So you see a significant ohmic drop. This is this paper, like the early operando papers, they already show that. If you start getting really thin layers, then your properties are gonna have all these effects of confinement, and then, a non-mic drop here from thicker liquids to thinner. So you have to be careful, or at least aware of this. Okay, another problem that you have when you want to do operando, and here you can see it with EELS, is that you create bubbles. So because of these small volumes, so you start going to very small volumes because you want to do a spectroscopy, then this bubble can accumulate in the area, and you can lose a little bit the potential window for operando experiments. So this is something that can happen, that the electrolyte solution detach from the surface of your electrode. So this is something that you have to be aware of. So you start getting to very small volumes, and then you have this accumulation of gas that can be, if you're doing electrocatalysis, then it can come from electrolysis of water. But if you can also do it with electron beam, we will see in the last talk. And what they usually do, so these are the two ways of forming bubbles, electrolytically and then also with radiolysis products. And usually this is a review that I like, where they talk about this. And then what they usually do is like, well, flow. This is like what it is done now in the community, using flow to try to get rid of these bubbles. And also using the off-chip reference electrodes. So these, at least the reference electrodes, do not have this problem. Yes. There is a question.
Do you have the same problem with bubbles forming in the static liquid cells, or is this a function of the electric flow holders?
In which liquid cell?
Like the static liquid cells, like Sarah Haig's or Robert Klee's. And
Robert, yes. I mean, in the nanochannels you do. I can make you a beautiful spectrum of hydrogen really quick. No, yes, you accumulate. Flow helps with electrochemistry. Everybody that does electrochemistry has told me that in a practical way. Okay, and then I wanted to mention this. So there is people out there that do modeling of radiolysis, and they combine it with electrochemistry and so on. And this was a cell that was designed also to help with this problem. So you can use flow, but then this helps you with using the flow in a smarter way to get rid of these bubbles. And then there are some, you can commercially buy this with some of the vendors. So what it does is that your working electrode is going to be outside. No, your counter electron and reference electrons will be outside of this thin area. So this is the diffusion cell that they came out with, the normal flow cell, and then the diffusion cell. And then, so that means that you're going to have a much thicker volume of liquid, which is going to help with electrochemistry. But then your working electrode that you are going to be looking at during the experiments and doing the spectroscopy and everything can be in a thinner area. So this improves the conditions. And then gaseous products also are gonna slowly diffuse, but then as soon as they get here, because the flow is much, they're gonna be, so for the modeling, this would be an infinite, so they will be just flash away. So this is a smart way of getting, so minimizing this area, which is the observation area, and you don't really care what happens here, and so that the flow is much more effective for the bubble in the working electrode, and you can keep this thing, but then you have the counter electron and the reference electron with much thicker, and then your properties can be better. Okay, so now I have just 2-3 slides that this is a little bit of introduction for the next talk. So there is one thing that I haven't mentioned. I haven't gone through everything, all the technical part that has to be fixed, but then there is like, yes, these samples are very sensitive, and there is something that you see with the experiment that you are actually modifying the chemistry of the solutions with the electron beam. And these are examples of radiation damage. This is one where we are actually using this because we proposed it for accelerating damage. Then the next year, there was a paper in radiolysis that they proposed the same, and then they can see different things. They can see gas with chromatography, we can see the solid, but yet it is a way of looking at accelerating degradation of electrolytes to decide like which one is better. But if you want to do an operando or an in-situ experiment, these are bad news, because this means that, yeah, you're going to have really quick, because this is what it undergoes, is an accelerated degradation of things that you're going to see during your experiment. And this, this was an experiment where they did, they minimize so instead of doing continuous irradiation, they just took a snapshot of the process, and then they kept doing the experiment. So there was an Operando, they were applying a bias in the electrode, and then they look again, and if you do this sparse acquisition, when you minimize the exposure to your electron beam, whether, and you compare it with a continuous acquisition, you see that you are changing also the, what happened in your SEI layer in your dendrites. Okay, so usually, so it is necessary in most of the cases here to minimize the dose, and usually what you want to do is like, yes, maximize the signal, minimize the dose to have the best detector, and so on. And something that you can do is to calculate this type of things. So this is for rhodamine, but it is a solid sample. So you can calculate the critical doses for something that you see. You say, okay, I'm going to do my experiment in these electron beam, the electron optic conditions where I don't see the electrode degrading. It doesn't mean that nothing is happening, but at least you are selected something that you can observe, and you're trying to avoid to look at these processes. And this is, did I put, oh. Okay, yes. So these are different ways of doing this. This is from a review from Egerton. You can look at the loss of fine structure in EELS. This means you are breaking bonds. You're losing your nitrogen carbon bonds, and then you're losing, you can look at this. So what is the dose that I have? What is the budget of fluence electron dose that I have before I start losing my nitrogen carbon bonds? Or global, so fading of diffraction spots when I start losing the periodicity, and so on. So this is something that you can do, try to be in conditions where you minimize damage. But for some experiment, this is not enough. So this is a paper where they were trying to look at live cells. This is probably one of the most extreme cases, looking at an in situ movie of live cell in the electron microscope. And then what they saw is that the viability of the cells were order of magnitude below what one frame actually requires to do an image. So they said that, I think the title of this paper is something along the lines that imaging live cells in the electron microscope is probably impossible or something like that. It was like the title. And they give numbers for that. Okay. And then something that is important is for this type of system, is there anything that we can do? It's not very clear because there are not a lot of insight of what it is exactly the electron beam doing. We see that it's damaging things, but there is not a lot of information, well, experiments, there is information, but on what it is exactly that it's doing in our experiment. And in the next talk, this is my last slide. In the next talk, we are going to see that you can actually use EELS to look at this. So I'm going to explain a little bit what is the decomposition that happens in the microscope. So what usually happens outside the microscope, how it changes in the microscope, and then what you can do with EELS to look at these things and understand a bit what is going on in the microscope. This is going to be my next talk. And you can do it with EELS because you have all this energy range that you have seen in the previous talk that allows you to look at excited electronic state, ionization, this is the beginning of radiolysis damage, and then to the production of radiolytic species later on, and so on. So you can look at all these things using EELS. Okay, and these are the conclusions. So there is a lot of hardware development that has allowed us to be where we are now, so we can do EELS for looking at many properties of liquids. And yes, you have to be careful because some of these things goes in opposite directions. If you want to do electrochemistry or you want to do good spectroscopy, there has to be a compromise. And yes, EELS can help us understanding what the electron beam is doing, and this is going to be in the next talk. Yeah, thank you. So, there was a question? No?
Are there questions?
Probably you want to rest a minutes or not?
What?
Do you want to rest a few minutes, or you want to go outside, take a coffee?
Maybe everybody wants to, well, I don't know.
I don't know. Anyway,
Yeah, 5 minutes at least for people to breathe.
okay. But before that, so before you explain the experiments you perform, you make sure in advance to perform these experiments all of this, no?
You
So
what?
So before you do the experiments in water, for example, you make sure the thickness you have, that it's thin enough, that you don't have bubbles, then
But anything you measure, you're gonna irradiate. So sometimes yes, and sometimes you want to do the thing first and then check all these things after.
okay.
Yeah, because in the nanochannel, for instance, you have two areas in some of them. Some of them is only one area, and these are connected. So as soon as you start degrading things, it's gonna diffuse, and then there is a history, so it could modify your next experiment. So if you want to make sure that you don't have an influence from one experiment into the next one, and you have a liquid that is connected, then you need to try to make the first experiment count. So usually what I do is try to find the conditions in the first area. First, I try to do an experiment right away. It never works because the focus is not there. Yeah. But then you try to find the conditions, and then the first experiment, you try to make it perfect. And then after, you start changing conditions and that, but you know that it's going to be affected. It's just that.
Okay. So,
Yes.
It's always changing.
With the flow and everything, it's always changing. In liquid cell electron microscopy, it's dynamic. So focusing on some conditions will never work because 5 minutes later, you'll not have the same conditions in terms of liquid, in terms of whatever reactions you have, radiolysis, no? This is really tricky to.
Yes, it is. In our case, we try to compare. So we try to change only one thing at the time. So we try to keep everything. But yes, in most experiments, you have to find every time. But these are like low dose experiments. You try to set things here really near, so it's similar, so that you can in an area. But with a liquid, it's difficult because they diffuse. So
Patricia, thanks for the presentation, but you have been mentioning many times that you have bubbles in your liquid, forming bubbles. Could you just explain me why are you forming bubbles in the liquid?
yeah, we're gonna see that in the next talk.
Okay.
Yeah, or
Because I mean, it's a matter of why the bubbles appear. No, it's just air or oxygen which is dissolving the liquid. Can it be removed before putting the liquid inside, or is bubbles of gas that are formed during the radiation? So you mentioned several times, and I couldn't say, well, from where it comes, no?
For electrochemistry, if you are doing electrocatalysis, sometimes you can split water with the electric field, but then you also do that with electrons. So any radiation, even with gamma ray or X-ray. So if you go through water, yeah, you're gonna, a part of the energy that goes is gonna be absorbed by the water molecules. But I'm actually gonna start with that in the next talk. But yes, you decompose part of the molecule. And then some of them form bubbles. You end up with molecular and radicals.